Right, so now it's time for the worked examples, and we can put some numbers to this now. So we have express root 2 multiplied by sine x plus cos x, and we have to write it in this form that we have just introduced today. So this form, and notice the conditions. So alpha is going to be an acute angle. That means we can find it on our calculators without too much hassle. So it's a number, it's non-zero, of course, but it's acute. All right, it's between 0 and pi over 2. And we also know that r is going to be a positive value as well. And remember that r will determine the scale factor of the stretch, won't it? So r, as it's the scale factor, it's that constant, you'll know that the minimum value will, of course, be negative r, and then the maximum value would be r. All right, so that's just something to bear in mind. So how do we go about doing this? Well, we just apply all the same rationale that we saw in cases 1 and 2. So we start off with the form that we have to write it in, which is this. And I'm going to write that out first. Then I'm going to break it open using the compound angle formulae. So if I start over here, we've got space to do a sketch later as well. So we've got r sine of x plus alpha, and we're going to use an identity. So that's going to be identical to r, and then we're going to break it open as we saw earlier. So that's going to be sine x cos alpha, making sure we use the correct identity, added to cos x sine alpha. They just swap around. Okay. And notice I'm not trying to memorize whether it's tan of A over B or B over A. I'm not trying to do that. I'm just going through the steps carefully, and I'm applying the identities as carefully as I can. And I'm going to let the identities do the work here. All right. So all that is identical to all that. Okay, as I stated earlier. Let's multiply through by r now. So this is identical to r sine x cos alpha plus r cos x sine alpha. All right. Now, if we go back to the question, we're told to express this unusual, it looks unusual at first glance, doesn't it? Because you've got the root 2 multiplying all this. But it simply means that the a and the b are just going to be root 2. I can quite easily just rewrite that as root 2 sine x, let's do it up here, added to root 2 cos x. That's all it means. So that means that if I equate the coefficients, so I'll do this in a different color so it stands out a bit more, that means that r and cos alpha for the sine x term must correspond to the root 2 that I've just written here. Okay, so we can write down our first equation. So that's going to be r cos alpha is going to be equal to root 2. We have a value for it, so we're going to call that equation 1. Okay, and similarly, if we look at the second term, we've got r and we've got sine alpha, and they must correspond to the coefficient of cosine, which is root 2, and it's positive all the way, so there's no need to worry about that. So we've got r sine alpha is also equal to root 2, and we're going to call this one equation 2. All right, good news. And we can use the tan identity now. So we can now say, by dividing equation 2 by equation 1, and I do it in that order because I want to create tan. Remember, tan is sine over cosine. So we get r sine alpha divided by r cos alpha must be the same as the right-hand sides divided by each other. Well, there's just root 2 over root 2. So that's going to simplify to 1. Okay, so let's just acknowledge the cancellation, show that we understand what we're doing. So the r's cancel. R is non-zero, of course. It's positive. We have sine alpha over cos alpha, which is, of course, tan. So I can now replace this with tan alpha. And root 2 over root 2 is, of course, just 1. And if you want to use your calculator, you can. But if you know about your right angle triangles, if you've got a tan of 1, it means you've got not an equilateral, a right isosceles triangle. So alpha must be 45 degrees, but we're doing it in radians, so that's going to be pi over 4. Okay, you might just want to verify that on your calculator. In fact, why not? I'll just do that. So I'll just do shift tan of 1, just in case you're like me and you just want to double check everything. Yeah, pi over 4. Okay, so we've got alpha. That's really good. So let's put that in a box. So we've got our first result. So we know that in this identity, or in this expression here, I should say, the alpha part is going to be pi over 4. It just remains to find out what r is. Now, you can use the sine squared plus cos squared identity, but you may have been convinced by just using the Pythagoras' theorem. All right, so we can say that a is equal to root 2, and b is also equal to root 2. So from the previous work we've done, and we know that r squared is equal to a squared plus b squared, or you can just say r is the square root of all that if you want to go straight ahead and do that. So therefore, r squared is just going to be, now I'll do this properly, I don't want to cut corners with this, root 2 all squared, that's a, plus, again, root 2 all squared. All right, and if you square a square root, they're inverse functions, aren't they? Sort of. So you can get 2 plus 2, so that's going to be 4. Now that's r squared. So therefore, r is simply going to equal the square root of that, which is 2. So r, of course, is a positive value. So it's not plus or minus. That's the final bit. So we've got r. Most people like to work out r first, in fact, because you can do it directly just using these values here and here. You just apply Pythagoras' theorem to them, assume they're the shorter sides, and hey presto. Right, okay, so that means we can now write down the form of the expression, and we can sketch the graph, hopefully. So the form is going to be y is equal to 2, that's r, multiplied by the sine of x plus pi over 4. Great, and these are the two values that I've found. So there's the alpha inside the bracket, and there's the r that we've just used. Okay, there they are. Right, so that's part A finished, and then it says hence sketch. So hence means use your result. And we've already mentioned as well, haven't we? The minus r and the r, that tells us the range of the function straight away. So we know it's going from -2 up to 2 because of that scale factor stretch. All right, so we have to sketch it within that specified domain. So you could go ahead and do part C straight away if you like, but I think to get the x component of it, the x coordinate, I should say, it's probably better to do the sketch first. So we're going to sketch for the domain specified, and we're giving you space to do this. So from 0 to 2 pi, use all the space you've given. like that. Okay, so what I've done to save you the grief of watching me draw those axes, I've just done the axes from 0 to 2 pi as specified, and I've also I've not sketched the final answer yet. I've just sketched the graph of y equals sine x. That's the parent function, just so we can get a grasp or a grip on the transformation that's taken place. So from 0 to 2 pi, so that's the domain that we're working in, as it states here. Remember, always read the question really carefully. And we're asked to sketch that harmonic function, but obviously we're going to use the form that we've the rewritten form that we've just been doing in part A because of the hence part of the question. Right, so we have to transform this. Now, we go back to what we deduced earlier. Having the plus pi over 4 inside the bracket is telling me I'm going to have to translate my parent function by pi over 4 in that direction because it's inside opposite. Okay, so that seems fine. And also because of the 2 here, this is going to stretch vertically, which we knew already. That's the easy bit. So I just need to know where all my points of intersection are, my maxima and minima. So everything shifts pi over 4 to the left. Okay, so the first thing to note is that this origin is not going to be a point of intersection anymore. So we can't deal with that just now. But what I can do is this point here where I have a point of intersection at pi, if I move by pi over 4 in that direction, then obviously my point of intersection is now going to be here. Okay, my maximum was originally at pi over 2. Okay, that's no longer the case because it has to be translated in that direction. So it's now at pi over 4 and it's going to be at 2 simply because of the stretch. Okay, so this seems to be how it's playing out. It might also be a good idea to figure out where the y-intercept is going to be. Okay, we'll do that in a moment. All right, so the other x-intercept is, of course, at 2 pi. So we now need to translate that to 7 pi over 4. Again, it's moving in that direction by pi over 4. Okay, and I'll just label that as well. You don't need to write this on your sketch, but it's just to show you. And the minimum value, which was at 3 pi over 2, is now going to be at 3 pi over 4, and it's going to be at -2. So it's going to be somewhere down there. Right. So let's figure out where this y-intercept is going to be. All right. So if we just do just a little bit of work down in the bottom over here, I'm just going to box this off just so we can figure out the y-intercept. So obviously the y-intercept is when x is equal to 0. Now, when x is equal to 0, I'm going to be calculating y as being 2 multiplied by the sine of pi over 4. Now, the sine of pi over 4, again, you can do it on your calculator, but it's the right-angled isosceles triangle with the 3 sides, 1, 1, and √2. So the sine is going to be 1 over √2. And if you multiply that by 2, you've essentially got 2 over √2. If you rationalize that, 2 over √2 is just simply √2, which is about 1.41. So that's where my y-intercept is going to be. So I can indicate that on my graph about 1.4. So it's going to be about here. And I think I'm in a good position now to sketch this. So let's do it. What color shall I do? I'll stick with the pink so it stands out. So hopefully I can get through all these points. And then it's going to go up a bit here as well to get up to 2 pi. So that's my attempt. Maybe yours is a bit better. So that's going to be 2 sine of x plus pi over 4. Now, so there's our sketch. We've got all those major points, the maxima, the minima, all labeled. So we have to write down the minimum value. Now, there's only one minimum value in this interval, and state the value of x which it occurs. Well, we we did quite a detailed analysis of this sketch. We know where all the main points are going to be, and we've already specified where the minimum is. Okay, so the minimum is obviously going to be at 5 pi over 4 because it was shifted, wasn't it, by pi over 4 from 3 pi over 2. And it's going to be at the point, the y value -2. So we'll just state it. I'll just state it on the graph so it's clear. So the minimum occurs at 5 pi over 4. And the value is, of course, -2. So that's why it's a write down, because you can literally just write it down from your sketch. All right, so for worked example 2, we've got something slightly more involved in this situation, so we're going to have to use our brains a bit more here. We've got this expression. Now, it's in terms of 2 theta. Okay, I'll get onto that in a minute. And then we're asked to write it in this form, r cos of 2 theta plus alpha. And we were given the usual restrictions on r and alpha, of course. So r is going to be a positive constant, and alpha is going to be a non-zero acute angle. And we have to give alpha to 2 decimal places. So it's in radians, of course. Right. Well, this 2 theta business, I think it looks a little off-putting, doesn't it? Because you'll be thinking about double angle identities and the like. But you notice how it repeats throughout these forms. So in the harmonic form and in the r cos form. So what that means is you can call the angle anything. It doesn't matter as long as you're consistent. So I can just go straight in and use the identity. And it's, in a way, it's there to put you off. But there's a bit more to it than that, as you'll see. Perhaps not in this lesson, but later on. Okay, so if I write the identity out that we're going to use, it's in the cosine form. So it's r cos, and it's going to be 2 theta plus alpha, like that. Right, now I'm going to be careful here with this identity because it's the cosine identity. And I've got to be cognizant of the fact that I've got 2 theta here and not x or just theta. So I'm going to be really, really careful with this. Fingers crossed. So in the cosine form, we're going to have cos of 2 theta multiplied by cos of alpha. And because it's added, the cosine form, you'll notice, is the opposite. So it's going to be subtract sine of 2 theta multiplied by sorry, nearly did it wrong. I think, Mr. Brockway. Sine alpha. Right, there we go. I would just take a moment just to double check that, because that's exactly what I'm doing now. So have I used the identity correctly? So we've got the cosine of all that must be identical to all this stuff here. Right, it looks fine to me. So let's proceed. Now we multiply everything by r, and then we can compare coefficients. So this is going to be identical to r cos of 2 theta, don't forget that, multiplied by the cosine of alpha, subtract r sine of 2 theta, multiplied by the sine of alpha. All right, so let's have a look at what our A and our B are in this situation. Well, if I write them in, you can see that A here is, of course, 5. And the B, I'm going to just call it 12 at the moment. We've got a negative there. We'll talk about that in a sec. So that means that when I'm comparing coefficients, as I'm going to do now, the R part and the cos alpha part must correspond to the 5 up here, okay? This 5. So let's write down our first equation. So we have R cos of alpha must be equal to 5. Okay, all that is just comparing coefficients. They're the coefficients of cos 2 theta, aren't they? Okay, so we'll call this equation 1. Okay, and let's apply the same rationale to the sine 2 theta term now. So this time we've got r there. We've got the negative there, but that's okay. We have a negative up here, so they correspond. So the r sine alpha must correspond to the 12 up here because I've got 12 sine 2 theta. Yeah, I hope this is making sense, guys. So we've got r sine of alpha is equal to 12. Yeah, no negatives. And that's equation 2. Now, we've done this a few times. We can now apply our identity. And if we do equation 2 divided by equation 1, then it should be plain sailing, at least for the time being. So we're going to have r sine alpha divided by r cosine alpha is equal to, and divide the right-hand sides of these equations. That's going to be 12 over 5. Okay. Now, let's have a look at the cancellation. Just acknowledge that that's going to be the case. That's going to be 1. That's going to be 1. And we have tan alpha equals 12 over 5. Tan alpha equals 12 over 5. And you'll notice this is a Pythagorean triple, well, in the making. So you've got two shorter sides of 12 and 5, which give you a hypotenuse of 13. But we don't need that at the moment. So therefore, alpha is going to be the inverse tan of 12 over 5. And you can do this on your calculator. There's no need for a cast diagram or anything like that, because it states plainly here that alpha is an acute angle. Okay, so no need to worry about that. So you can get your calculator out. Let's do that. Let's get rid of this. Okay, so inverse tan. We're on radians, of course. Make sure you've got your calculator on the correct setting. So shift tan 12 over 5. Just come out of that fraction equals okay. And we need this to 2 decimal places. So that's going to be 1.18. So I'll just write that in now. So that seems fine. So this is equal to 1.18 to 2 decimal places. Okay, and I'll just highlight that because it's probably going to get lost at the bottom of the page. There it is. Okay, so we've got our alpha. Great news. And now we know how to find r. And like I said, some people prefer to find r first. And I've already alluded to it. The answer is 13, of course, because it's a Pythagorean triple. But let's just do the working out. So I think I'm just going to box this bit off. So I've got a bit more space to work, or a clear space to work. So we know that r squared is just going to be a squared plus b squared. And in this instance, it's going to be 5 squared plus 12 squared. Well, b is, of course, 12 because we've got the, although it's negative, it doesn't make any difference at all. Because if you square a negative, of course, you get a positive. So the values themselves will be fine. Okay, and then that's obviously going to be 169. So therefore, r is the square root of that, which is 13. But you might have known that already. If you did, well done. Okay, so we'll make that look important as well. So we've got our r and we've got our alpha. That was our goal. Once you've got those, you can now write your expression in the form it's required. I'm going to do that next to the question, so we've got a bit more space. So the form we want is, of course, this. So it's going to be 13 cosine of 2 theta, okay, plus alpha. Now, alpha, of course, is 1.18. It doesn't look very nice, but that's what we found. So that's the form that it's required. Now, what do we do with this? Well, if that's part A done, it says hence or otherwise. Well, remember when you see a hence or otherwise question, you immediately dismiss the or otherwise bit. Just put a line through that. And we're going to use what we've just found to solve in the interval from 0 to 2 pi this equation. Right. Now, notice this equation is very, very similar to the 5 cos 2 theta. So this is why it's a hence question. Subtract the 12 sine 2 theta. It's very similar, isn't it? All right. And that's equal to, is going to be equal to 2. Now, I'm not going to put equals 2 because if you'll notice, I just undo all that. Let's just take this equation. Let's just divide all of that they've given us, all of this. Let's divide the whole thing by 2. Okay, there's factors of 2 in every term. Let's just do that. What do we get? Well, we're going to get 5 cos of 2 theta. Okay, divided by 2. Subtract 12 sine of 2 theta is going to equal 1. So I've just divided by 2. Okay, and lo and behold, that's the form that we've rewritten. So therefore, all we have to do now is replace all of that with what we've just discovered. So 13 cos of 2 theta plus 1.18 equal to, well, 1. Okay, so we have to solve that equation in this interval here from 0 to 2 pi. All right, so that's what we're going to do in the next part. So this is a classic trig equation question. So the first thing to do is let's make a nice substitution. So I'm just going to partition this. So let's say let big X equal this rather nasty looking angle 2 theta plus 1.18. Okay, so we've got that, and we can now rewrite the equation as 13 cosine of big X is equal to 1. So therefore, the cosine of big X is going to equal 1 over 13. Okay, that's good. So now we can find our principal angle. So principal angle will do the inverse cosine . So remember, the principal angle is you imagine, if it's not positive already, you imagine that value is positive. You do the inverse cosine or the inverse sine, the inverse tan, or whatever it is, and it gives you an acute angle which you can place on your cast diagram in the correct quadrants. So if we do that, I'm just going to have to use my calculator now. Okay, so this is going to be, if I just reset the calculator, it's going to let me, yeah, good. So it's going to be the inverse cosine, it's set on radians, of course, shift cos 1 over 13, just come out of that. Okay, we get 1.494. So I'm going to write that to 3 decimal places, I think, because the accuracy for alpha was 2 decimal places, and I want to maintain accuracy at the end. So we'll call that, let's get back on the drawing function. So that's going to be 1.494 radians. Okay, so that's our principal angle. Now we need to add this to the cast diagram. Okay, cosine is, of course, the positive, so we're going to put it in the positive quadrants where cosine is positive. Before we do that, of course, we need to make an adjustment to our intervals. So let's do that next. So we're going to adjust the interval. So it's a slightly awkward one, this one, because the interval is, it's not just been doubled. We've got to also add 1.18 radians to it. So at the moment, we have an interval between 0 and 2 pi for theta. So I simply have to double it. So multiply everything by 2, first of all. So that's 4 pi, so I have to go around twice, essentially. And then add the 1.18. So that's going to be from 1.18 radians add that to the 2 pi in the middle. And then if I do 4 pi plus 1.18, I'll just leave it like that for now. It gives me a better sense of what's going on rather than just writing a decimal down. So that's my interval. And remember, of course, that this rather nasty looking part in the middle here is just going to be x. So you can write this interval in terms of x, and we solve for x. And when I say x, of course, I mean big X. So this is the interval we're working in. Right, so it might be worth just highlighting that as well. Okay. Okay, just to summarize where we're up to, we made a substitution for 2 theta plus 1.18, and that was x. We are solving the equation cos x equals 1 over 13. We've got a principal angle of 1.494 radians. Now, normally I would do this in degrees, but we'll stick to radians in this case. All right, it's about 85 degrees, 1.494. And then the interval is specified just below, between 1.18 and 4 pi plus 1.18. Right, so to solve this trig equation, we need to do the following. So we need a cast diagram. I'm just going to draw the cast diagram here. Okay, and just label it as normal. And we are obviously dealing with positive value of cosine. This is 1 over 13. So that needs to go in the positive quadrants. So we'll add that to the positive quadrants. There and there. Okay, that's where cosine is positive. And this is worth 1.494 radians. And this is 1.494 radians as well. So this is where a calculator will probably be handy. So we'll get the calculator ready. I'll put it over here. All right, and let's just read off all the answers. So the first one, this is for x, of course. So the first one, of course, we're starting at 1.18. Now, just to be clear about this, 1.18 would be slightly less than the 1.494. It would be about here, maybe. I mean, obviously these are way off. They're not accurate, but it would definitely be less than 1.494. So the 1.494 is within the range. So that would definitely be our first angle. Okay, which is the principal angle, and we've got to go around twice because it's 4 pi. Now, the next one will be 2 pi subtract the 1.494. So we can use our calculator for this. So 2 multiplied by pi, just to be exact, which is that, and then subtract 1.494. And we get 4.789. Okay, so we'll leave it at that accuracy. So that's 4.789 for the next angle. Okay, so that's one full turn. So that's 2 pi radians we've covered so far. Then we have to go around again. So then I have to add 2 pi to 494. So we add 2 pi to both of these solutions. Okay, so just cancel that, and we do 2 multiplied by pi, and we add 1.494 like that, and we get all the 7s. 7.777. Okay, so that's that. So that's the on the second pass, and then we've got 4 pi subtract our principal angle. So 4 pi, and then subtract 1.494, and we get 11.072. So I'm maintaining the number of decimal places here as well. So that's 11.0724, or just 2, 3 decimal places. Now then, so that's going around twice. So now we're at 4 pi, but remember we're dealing with 4 pi plus 1.18. So could we squeeze in an extra angle? Well, the answer is, of course, no, because the next angle would be 4 pi plus that, which is obviously going to be greater than 4 pi plus 1.18. So we have four solutions to this equation. Now, we're not out of the woods yet, of course, because we need to find out what theta is. Okay? To do that, of course, we make the substitution back. So I'm going to take my x there, and I'm going to replace it with the 2 theta plus the 1.18, which is what x replaced. And that, of course, is equal to all the same angles that are given above. I'm not going to write them all out again because there's no point in doing that. So for each of these angles, I have to subtract 1.18 and divide by 2. So that's what I will do next. Okay, so I spared you all that laborious calculator work. I've given the answers to 1 decimal place now. So just to recap, I've taken all of these values, and I've basically subtracted 1.18 and divided by 2, and that will give you this collection of answers here. They're all given to 1 decimal place because that's what's required in the question. So my 3 decimal places was probably a bit OTT, but there's nothing wrong with being accurate if you can round at the end. So that concludes it. So that was rather an awkward trig equations question. So next we're going to look at something that will be more useful later on in this chapter. There's not much more to come, but it links to a lot of modeling, which is really important and maybe a feature of your exam. Okay, so for the last part, I've just given you a bit of a recap. Remember that we found that 5 cos 2 theta subtract 12 sine 2 theta can be rewritten as this single cosine, which we did right back in part A. So that's taken from this form which we expanded, and we found alpha and we found r. Now for part B, we solved an equation by substituting the 13 cos 2 theta plus 1.18 in for all this stuff here, and we solved the equation, and we got 4 solutions within the given range. Now for part C, we've got this function that's been defined. Now, if you look at the function, it looks vaguely familiar, doesn't it? We've got the bit we want, or the bit we're interested in, or we've been interested in for quite some time now, is sat right there. So the question is, can we state the maximum value of this function given the information we've got? Well, let's have a look at this, and we also have to state the value of theta at which it occurs. Well, let's do a substitution. I think it's pretty clear now that I can rewrite this as 1 plus. Now, the 5 cos 2 theta, we have a new way of writing it, of course, and I've just restated it below as well. Here it is. So why don't I replace all that with this cosine form? And we'll see what that does to this function. So it's going to be 13 cosine of 2 theta plus 1.18. Okay. And then all this is going to be divided by 2. Right. So that's interesting. So that's our f theta. Now, what I could also do is I could split this up into 2 terms. I could say, well, this is going to be a half plus, and I'll do it in a different color. We've got 13 divided by 2, haven't we? So that's going to be 13 over 2 cosine of 2 theta plus 1.18. And we're asked to find the maximum value first of all. Well, the maximum value, this is related to the range, isn't it? Okay. And it more importantly, it's the upper limit of the range. So can we find the upper limit of the range for this function? Well, indeed we can, because if we look at the cosine part here, the range is dictated by the 13 over 2, the coefficient of the cosine. It's nothing to do with the 2 theta plus 1.18 because that is an x transformation, or in this case, a theta transformation. So the range is not affected by any of this. Okay, that's superfluous at the moment. So we know that the range of values can be written fairly straightforwardly. Now I'm just going to do a bit of work on this just down at the bottom. So if we consider f theta and consider the maximum, so I'm just going to use a little subscript here, it's going to be when we have a half plus 13 over 2. And then remember that the cosine part, I mean, you can think of it like this as well. The cosine part of this function is sandwiched between -1 and 1. It's trapped, isn't it? Cosine graph always oscillates between -1 and 1. Okay, so the maximum value it can ever take is the 1 right there. Okay, so that's what I put in to this f max here. So this is going to be 13 over 2 multiplied by 1, the biggest value cosine can take. But you knew that already, because if you consider the 13 over 2, that's the scale factor multiple. So the 13 over 2 cosine function is going to oscillate between -13 over 2 and +13 over 2. So we just have to add these together now. So this is going to give us a half plus 13 halves. So it's just going to be 7. And that's the maximum value it can take. Now, this is where it gets interesting. So now we have to find the smallest positive value of theta at which this occurs. Right, so for this bit, we can actually consider this range of cosine. So let's just make a note here to find theta max. Okay, this is where this f max occurs. And it's the least positive value of theta when it occurs. Obviously, there'll be an infinite number of these, just as there'll be an infinite number of maximums. We can solve the equation. When is the cosine of 2 theta plus 1.18, when does this equal 1? Okay, the maximum value it can take. Yeah, we can ignore all the rest of it because that's just window dressing. We just need the cosine to be maxed out. So if we solve this equation, we should have the value of theta. So for this, we can use a cast diagram. Now I used big X before, so let's use Y. So let big Y equal 2 theta plus 1.18. Okay, and then we're going to solve cosine of big Y is equal to 1. Well, if you do that, your principal angle, so I'll just write as PA, is just going to be 0. Okay, because that's the 0 degrees. In fact, this is in radians, isn't it? 0 radians. Okay, so it's 0 radians because you know the cosine function begins at a maximum, doesn't it? So we've got that. So we know it's 0. So if we add this to a cast diagram, perhaps we can figure out what the least positive value of theta would be. So let's draw the cast diagram now. So I'm going to take this up here. I hope you've got enough space, ladies and gentlemen. So C, A, S, and T. Now 0 is quite difficult to add to this, but what I'll do, I'll cheat. I'll make an angle like that, but I'll just put 0 like that. Okay. And if we go around, obviously, anti-clockwise and just read off the angles in radians. For Y, I'm going to stop using red because it stands out a bit too much, I think. So the Y angles are simply going to be, well, 0, first of all, and 2 pi. Okay. Now, I don't think there's much point going any further, simply because one of those has got to be the least positive value of theta. Yeah, because I'm going to be subtracting 1.18 and dividing by 2. All right. So let's do that. So we can now replace the Y here with the 2 theta plus 1.18. And I just want to make this concrete so you can see what's going to happen. So we've got 2 theta plus 1.18 at a maximum must be equal to 0 or 2 pi. Now, straight away, you'll notice if you subtract 1.18 from 0 here, you're going to get a negative. And if you divide by 2, it's still going to be negative. So that one is pointless. So instead, we're going to solve the second equation where 2 theta plus 1.18 equals 2 pi. So let's do that. So your theta is going to equal 2 pi, subtract 1.18, and you divide that by 2. And you can get your calculator for this. So theta is going to equal 2.55 radians. Well, that's 3 significant figures. It doesn't specify an accuracy, I don't think. Okay, and this is less than less than 2 pi, of course. So I think that concludes it. So we've got a maximum at the first maximum, of course, as well. The first maximum occurs at 2.55, and the maximum value is, of course, going to be 7. Okay, and just to finish off this question, just thought I'd show you the graph of the function we've just been talking about. So it's defined over here. So it's a half plus the 13 cos, it's x in this case, because it's on GeoGebra, 2x plus 1.18 all over 2. You can see the maximum at the point B here. This is the closest maximum or the first maximum you get between, sorry, just get rid of that. Oh, never mind. So if you can sort of see what's going on, I can't scroll across, which is annoying, but if you'll notice, the origin is somewhere here, and I'm writing in the wrong pen again. The origin is somewhere here, and the first maximum you get to is, of course, at B. Now, what that means is, of course, if you look at the coordinates of the maximum, that's 2.557. The first extremum, as it's called, which is the minimum value, is at -6. Okay, so that's definitely the first maximum that we got to.